Hello YouTube. So a while back in my scientific realism series, I did a video on Kyle Stanford's argument from Unconceived Alternatives. It's a fairly straightforward argument against realism, the view that our best scientific theories are approximately true, and it goes something like this. The historical record reveals that there were equally good alternatives to the accepted theories of the past, but that past scientists failed to conceive of. So there are probably equally good alternatives to current theories that current scientists fail to conceive of, so we should not believe that our best scientific theories are true. Science is a very effective tool for deciding between competing theories, but obviously we can only compare those theories that we have actually conceived of. We can only test those theories that we have actually conceived of. The claim that a theory is true can only be justified if there is no potential challenger theory that is equally good or better. So, let's say we have some theory that accommodates all of our observations and it has various non-empirical virtues like simplicity. It's superior to the rivals that we've considered. But there is some other theory that we haven't thought of yet that performs equally well or better. If we knew of that theory, we would accept it instead. We just haven't conceived of it. I mean, the challenge to realism here should be obvious. The status of our currently accepted theories may change drastically once currently unconceived alternatives are appreciated. Scientists in the past thought that Newtonian mechanics was extremely well confirmed. They thought that was the best theory available until later scientists came up with general relativity, which accommodated the evidence better. Stanford thinks that we have similarly good reason to expect that contemporary scientists have just failed to conceive of potential alternative theories, or at least, at the very least, if you're a realist, it looks like you're going to have to rule out, or at least you're going to have to say that there's a very low chance that there are serious alternative theories, and what could justify that claim. Actually, there's a really fantastic example of this problem in the news right now. We've just discovered phosphine gas on Venus. Phosphine is a biosignature gas, and it's being produced in just the part of Venus's atmosphere that scientists had previously speculated might be habitable. Now, the research on this involved ruling out a whole bunch of other abiotic explanations of phosphine production. So it's not explained by volcanic activity. It's not explained by interaction of UV light with atmospheric molecules. It's not explained by interaction of lightning with atmospheric molecules. It's not explained by delivery from meteorites, and so on. The only process that we know of that can produce this much phosphine is life. But the key phrase here is that we know of, right? Maybe there's some other process that we don't know of. And until we actually image the microbes in a microscope or whatever, it looks like we're never going to be able to conclusively rule out these other explanations. So, we don't yet conclude that there is life. I guess the point is, look, this kind of thing actually applies to basically every scientific theory, right? For pretty much any theory, there might be other theories available that provide better explanations that we just haven't thought of. Now, this argument has been extended in an interesting way by Darrell Rowbottom in his paper Extending the Argument from Unconceived Alternatives. Rowbottom points out that theories are not the only entities in science that might be unconceived. There are unconceived alternatives to all kinds of elements in science, and all of these factors raise the probability that there are serious alternative theories that we do not yet appreciate. So all of these compound the challenge to realism. I actually did point out Rowbottom's extension in my original video on this, but what I want to do here is just look in more detail at the cases that he discusses. So, first of all, there are unconceived observations. These arise in various ways. For one thing, we are constantly confronted with new and unanticipated phenomena, which did not arise in theory testing, so are not linked to the confirmation or disconfirmation of any existing theory. Unexpected observations thereby lead to unexpected theoretical development. They can lead us to develop theories in directions that we just had never thought of before. Rowbottom cites the example of the discovery of deep ocean ecosystems around hydrothermal vents. Hydrothermal vents were predicted, but nobody expected to find flourishing chemosynthetic ecosystems with fairly complex life. And this discovery raised a puzzle. How could such communities be maintained? And this led to significant developments in our understanding of biochemistry. A few other examples some from astronomy, the detection of pulsars, the detection of fast radio bursts, the very recent discovery that rust is forming on the moon despite the absence of oxygen and water. The thing to note about these examples is that they're not simply surprising observations, right? The discovery of phosphine in the atmosphere of Venus, that was surprising. But that was found by scientists explicitly looking for biosignatures of life. They were explicitly testing the hypothesis that Venus might harbour life, and phosphine in the atmosphere was evidence of this. So this observation was surprising, but it wasn't an unconceived observation. They knew they were either going to find phosphine or not find phosphine, right? That they'd conceived of those two possibilities. An unconceived observation is an observation that prompts new theoretical developments without being related to any currently accepted theory, either as a confirmed or disconfirmed prediction. Like an unconceived observation is just something we stumble across in the course of other researches, and so it takes us in completely unexpected directions. Unconceived observations can also be a product of unconceived theories because observations may be theory-laden, and the necessary theory to conceive of the observations may itself be unconceived. So the key point here is that we need theories to provide interpretations of what we observe. Rowbottom gives the following example. He says, imagine that archaeologists are exploring the remains of an ancient civilization. One of the most prominent features of this civilization is their art. It involves many depictions of ducks, all in the same style. Ducks appear to have been very important to the people of this civilization. There are murals of ducks on their buildings, there are pictures of ducks buried with the dead. So the archaeologists think ducks must have had some special religious significance to these people. But eventually a new discovery is made. The remains of a previously unknown animal, a lagomorph, are unearthed in the area of this civilization, and people decide to call this animal the rabbit. So we're imagining that in this world, rabbits had become extinct thousands of years ago, so nobody beyond the ancient civilization had ever encountered rabbits before. And the point is, this discovery transforms the interpretation of the artwork of the ancient civilization. The images that were thought to be of ducks can just as well be interpreted as depicting rabbits. So it's proposed that these people actually worshipped rabbits. Now, if you consider the hypothesis, the ancient civilization worshipped ducks, well, we can see that the confirmation status of that hypothesis changes radically as a new theoretical interpretation of the observations of their artwork is provided. I mean, the hypothesis is initially very well confirmed, but then it ends up being rejected. Because they have a new way of thinking about what it is they're seeing. So, the key point then of all of this is the possibility of unconceived observations or unconceived interpretations of observations raises the probability that there may be serious unconceived alternative theories. If we haven't even made certain significant observations, then we cannot have developed theories to account for those observations. So if there are unconceived observations, we should expect that's going to raise the probability that our currently accepted theories are false. Next, unconceived models. In many cases, theories do not in themselves make predictions. Models must be generated in order to coordinate the theory with the world. An example given by Rowbottom is that of pendulum motion in classical mechanics. The initial models of the pendulum were highly idealized. In the simple pendulum model, idealized assumptions include that movement only occurs in 2 dimensions, that the cord on which the bob swings is massless, that there is no energy loss to friction or air resistance, that the gravitational field is uniform, and so on. Obviously, this model can be taken to approximate the behaviour only of a very specific class of real pendulum systems. It took a long time for classical mechanics to develop more sophisticated models that allowed accurate predictions of pendulum motion in a broad range of cases. As another example, consider Laplace's work on celestial mechanics. He showed that the simple inverse square law of gravity was sufficient to account for all of the data on planetary motion that was known at the time. It was a remarkable achievement. For instance, one of the central problems in celestial mechanics in the 18th century was the stability of the solar system. Given that there are many planets around the Sun, they're subject to mutual gravitational attraction, which disrupts their orbits. These perturbations are weak, obviously, but in the long run they may accumulate and destroy the system. Indeed, astronomers had already observed what they called the long inequality of Jupiter and Saturn. Essentially, Jupiter was accelerating, moving closer to the Sun, Saturn's motion was retarding, and Saturn was moving further away. In the long run, Saturn would be lost from the solar system, while Jupiter would move inwards and seriously perturb the orbits of the inner planets. Newton's solution to this was simply to say that occasionally God intervenes and restores the solar system to its proper state. Not a particularly satisfying answer. Laplace was able to show that the inequality is cyclic, with a period of about 929 years. So in the long run, the system is in equilibrium. It's stable. The key idea is that Jupiter completes 5 revolutions around the Sun about every 59.3 years. Saturn completes 2 revolutions around the Sun about every 59 years. So the point of their conjunction occurs about once every 59 years. The effect of their interaction will be strongest at this point, obviously, because that's when they're the closest. But the point of their conjunction moves around the Sun, and once it's moved halfway around the Sun, the effect of their interaction will reverse. So he developed a model of orbital interactions, which was able to show that actually, this change in the orbits of Jupiter and Saturn is cyclic, and the system is stable. And the model turned out to be predictively accurate. It was applied. I think actually they then later observed that the motion of Jupiter did indeed change in line with Laplace's predictions. Anyway, our judgments of the predictive power of theories are contingent on the available models in those theories, the models that allow us to apply the theories to particular cases. Classical mechanics has remarkable predictive power, but it took hundreds of years before the full range of its applications were realised. Part of what made Laplace's work on the Jupiter-Saturn problem, among many others, possible was that he abandoned Newton's geometrical treatment of classical mechanics and instead based the theory on calculus. So only with this theoretical innovation could the scientists build such a striking range of mechanical models. In every theory, like the laws, the laws of the theory are often insufficient to generate predictions. If you want to get the predictions, you've got to have models that tie the theory to the world, and that takes a lot of time. It takes a lot of development. So suppose we have 2 theories, T1 and T2. We've conceived of both of these theories in the sense that we understand the laws, we kind of understand how they work. And we've evaluated the predictive power of these 2 theories. But whereas T1 has well-developed models providing powerful predictions, the models of T2 are undeveloped. So T1 appears to be the more powerful theory. If we had instead put the effort into developing models for T2, it would appear more powerful than T1. Conceiving of a theory isn't enough. We need to conceive of the models as well. And as we generate more models, as we come upon models that we currently haven't conceived, we should expect that the evaluation of our current theories will change. Next, there are unconceived methods. This includes potential types of experimental setups and potential methods for data analysis. Take blind and double-blind experiments. Today, these are absolutely central in fields like psychology and medical research. Obviously, it's always been possible to perform experiments like this, but the first recorded use of these techniques was in 1784 in studies of mesmerism in France. Scientists could have used these methods any time, but apparently it just didn't occur to them to do so until just a couple of hundred years ago. Or take the development of probability theory and statistics, tools like analysis of variance and Bayesian techniques. Look across the history of science, you will find that we are constantly developing new methods. Theory assessment depends on the evidence available, on the experiments we have performed and the methods of data analysis that we have applied. But the history of science shows that we're constantly developing new ways to do this, and in that case, how can we rule out that there are important methods or useful methods that are currently unconceived of, that would change our evaluation of current theories? There may be new ways to design experiments, new ways to analyse data that would lead us to accept different theories. We can see the potential impact of unconceived methods by thinking about the limits of those methods that we do already use. So let's look at microbiology and the attempts to characterise microbial diversity. The current tools that we have for analysing microbes are quite limited. So there are three methods discussed by Carol Cleland in her book, The Quest for a Universal Theory of Life. First, there is microscopy. It's well known that superficial morphological similarities can hide significant differences in the molecular structure, the molecular architecture and molecular processes of microbes. You can't distinguish bacteria and archaea just under a microscope. They both share a prokaryotic cell plan. They both essentially look the same, right? But they're actually totally different domains of life. Indeed, archaea may be more closely related to eukaryotes than they are to bacteria. Eukaryotes include, the plants and animals and stuff, the sophisticated multicellular organisms. Archaea may be more closely related to us than they are to bacteria. So these are radically different domains of life, but that's not revealed by microscopy. Second, there is cultivation, which involves cloning a single microbe under controlled conditions, so you get loads and loads of different copies of it. Cultivation is one of the most powerful tools of microbiology. Our most detailed knowledge of the microbial world comes from those microbes that have been cultivated, because it provides us with large numbers of identical microbes, and that allows extensive study of their genetics, their metabolism, and so on. Unfortunately, cultivation techniques have a very limited applicability. Arguably less than 1% of bacteria and archaea can be cultivated. In some cases, this is because the uncultiviable forget it. In this case, this is because the microbes are dependent on complex, poorly understood environmental conditions. In other cases, it may be that they require extreme environmental conditions that are difficult to replicate in a laboratory. And almost all microbes are dependent on interactions with broader microbial communities. It makes it very difficult to grow just one single species and just copy a clone. So cultivation is very limited. Third, there are metagenomic methods. These involve extracting DNA and RNA directly from the environment and then copying these samples using tools like polymerase chain reaction. Now, there are a whole bunch of different ways of doing this, but polymerase chain reaction, for example, requires primers. Primers are small pieces of synthetic DNA that attach to the target sequence to initiate replication. Now, to get the right primers, we need to have prior knowledge of the target sequence. So that severely limits the use of polymerase chain reaction in detecting novel genomic sequences. The primers used for bacteria can't detect archaea, so the first polymerase chain reaction studies of microbial diversity missed the archaea. There are, of course, other tools for exploring the microbial world, but the point is, actually, all of these tools have similar drawbacks. Often they can't be applied without some prior knowledge of what it is we're looking for. Cleland even suggests that for all we know right now, there might be a shadow biosphere on Earth, life that arose independently, that shares no common ancestor with life as we know it, and that operates with a radically different biochemistry to known life. The current methods for analysing microbial diversity may well be insufficient to discover this, even if it did exist. I got a video on the shadow biosphere. I think it's called "Is There a Shadow Biosphere?" if you want to learn more about that. But the point is, it may be that our current methods for analysing microbial diversity are actually really, really limited, and maybe with new methods in the future we would transform our theories of life. Finally, there are unconceived theoretical virtues. A theoretical virtue is an aspect of a theory that counts towards its acceptability. It's an aspect of a theory that is taken to indicate the truth of the theory. Thomas Kuhn, for example, suggested that almost all scientists take to be virtues that almost all scientists take are accuracy, consistency, scope, simplicity, and fruitfulness. Scope there means like explanatory scope, so the theory applies to a wide range of things. Fruitfulness means you can basically like apply the theory and develop it, and develop new theories from it. They will prefer a theory that scores well on these values. Obviously, predictive accuracy and consistency are important. We want our theories to correctly predict what we observe, and we want our theories to be internally consistent. It's obvious why those might be taken to indicate that a theory is true. But these aren't the only factors that scientists tend to consider. Many people suppose that simplicity indicates truth. This is expressed in Occam's razor. Other things being equal, simpler theories are to be preferred. We prefer theories that postulate fewer entities, fewer causes, that involve more straightforward laws. Or scope. We take it that a theory is more likely to be true if it has wider explanatory scope, if it explains a wider variety of phenomena. Many of the most important steps in the development of science have been the unification of seemingly unconnected things, as with Maxwell's unification of electricity and magnetism. Now, there are three ways in which unconceived virtues pose problems. First, how can we rule out that there may be other theoretical virtues currently unconceived that are also indicators of truth? So take two theories, T1 and T2. We judge them to be equivalent in terms of accuracy, consistency, scope, and fruitfulness. But T1 is simpler than T2, so we accept T1. However, suppose there are further theoretical virtues unconceived of on which T2 performs better than T1. Had we conceived of these virtues, we would have accepted T2 instead. The question for the realist is going to be, is there any way to show that the probability of unconceived theoretical virtues is low? Is there any way to show that the theoretical virtues we currently know of and that we currently use as standards to judge our theories, is there any way to show that that's it? How would we go about showing this? Second, the weights that we place on these virtues can change over time. A good example of this is a virtue that's not on Kuhn's list, but that of intelligibility. Many past scientists required that theories be intelligible, that is, that we be able to visualize the causes and mechanisms proposed by the theory. The theory needs to, we have to be able to generate visualizable models. So the 17th century mechanists are the best example of this. They interpreted this in a very strict way. On their view, the material world is composed of small particles called corpuscles, and all acceptable theories need to specify how the phenomena that we observe emerge from the interaction of these particles. And it's ideally, we have to provide explanations which actually show how you can get to phenomena like gravity just from the pushing and pulling of different particles, right? You have to, it has to show how you've got one billiard ball or one atom hitting another, and through interactions like that you get all of the phenomena we observe. Now, in modern science, since the discovery of bizarre behavior on the quantum level and the development of like the extreme mathematical abstractions of theoretical physics in things like string theory, well, there's really relatively little weight placed on intelligibility. Theories no longer need to provide us with visualizable models. And we might similarly wonder if features of theories that we currently take to be theoretical virtues are actually not so virtuous, right? This is just another example of how our judgment of what counts as theoretical virtues may change. And that, of course, will change our evaluation of the theories. A third point is that how these virtues are manifested is up for dispute. So exactly what features count as exhibiting these virtues is debated. Basically, just as there are unconceived theoretical virtues, there may be unconceived ways of interpreting the virtues that we already know about. So take simplicity. We've long used simplicity as a criterion for theory assessment. Obviously, Occam's razor goes back hundreds of years. But our ways of interpreting and measuring simplicity have changed over time. For example, a central measure of simplicity in information theory is Kolmogorov complexity. But this was proposed only in the 1960s. Essentially, the idea of Kolmogorov complexity is that the amount of information in a string of symbols is defined by the size of the minimum length computer program that would be able to produce that string. Or to put it in a more intuitive way, you have to ask how much compression of a string is possible, right? The more compressible strings are simpler. So if you take this string, AB, 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 repeated over and over, that's repeated 22 times, well, you can compress that. You can just say AB times 22, and that's 5 characters. And obviously we could keep extending this. We could keep saying AB, AB, AB. We'd still have a very short description, right? It could be like AB times 1000. That's very compressible. On the other hand, consider this string. Well, this isn't compressible. The shortest description of this string is just to write down the string itself. So the key idea here is compressibility of, like, the compressibility of strings of information. And we can apply this to scientific theories because theories can be thought of as specifying patterns in the data that they're used to explain. The more that a theory compresses the data, the simpler that theory is. Now, actually, there are numerous problems with applying Kolmogorov complexity to scientific theories, but, you know, that should give you some sense of, like, different ways of thinking about simplicity. Other formalizations of simplicity in information theory are minimum message length and minimum description length. And here is a brief list of some more general ways that simplicity might be interpreted. I've taken this from the Internet Encyclopedia of Philosophy article on simplicity. So there's a whole bunch of, and these are just 5. There are actually more listed there, but these are just 5 different ways of thinking about simplicity. And perhaps there are still other ways of conceiving of simplicity, currently unconceived, that would affect our judgments of the status of theories. Obviously, before the 1960s, before Kolmogorov complexity was proposed, nobody would have been able to use that as in a criterion of theory assessment, right? In the same way, there may be further ways of interpreting simplicity that we haven't conceived of yet that would change our evaluation of our theories. So, yeah, those are a whole bunch of different ways, of different items in science which are subject to this problem of unconceived alternatives. And all of this ends up, it compounds the problem for the realist. It suggests that there may be alternatives to our currently accepted theories that are just as good as our currently accepted theories, but that, like, either we haven't thought of, or even if we have thought of them, we haven't developed them properly, or we're just not in a position to evaluate them properly, and our evaluations may change in the future. So that's all. Thanks for watching.